So let's look at this example one. So we'll go back to the one of the exercise example, and then we'll move on to the another subject today. Okay. So this was the one of the question. I say it's very complex, so I just left it over in the last actual class. So let's look at it. So this is the one of the real problem we have encountered in the 1980 when we really applied so-called molten carbonate fuel cell. So this is the one of the fuel cell which is commercialized so far. Okay. So probably heard a lot of the so-called oxide fuel cell. There's many different kinds of fuel cell and battery and all this kind of thing. And there's two most well-known fuel cell. One is so-called molten carbonate fuel cell, MCFC. We call it MCFC. And then the other one is solid oxide fuel cell, SOFC. These two is most commonly, most well-known. And so far, MCFC is really applied, really actually commercialized. Even SOFC is not very well commercialized so far. Okay, so MCFC was actually developed already in 1960. Okay, and it took about 40 years after that to really commercialize it. And there's one of the actually key problem here, and this was the one of the key problem. People was interested to learn actually this kind of fuel cell for a long time. Once you actually built it, whether this actually the machine will produce electricity for the long time, almost same level of the electricity for a long time or not. That actually relates to actually this thermodynamic problem. Okay, let's look at this one. So we have the molten carbonate fuel cell, which is developed in 19 whatever. And electrolyte is the Li2CO3 and the K2CO3, and with a mole fraction of K2CO3 about 0.38. And the operation temperature is around 650 degrees Celsius. The activity of K2CO3 in this binary solution, binary liquid solution, is 0.075. Okay? And the electrolyte is in equilibrium at 650 degrees Celsius with the gas phase, because the gas is the inserted inside of this fuel cell, and that actually make actual chemical reaction. And the inlet gas is pH, and inlet gas is H2 and H2O and CO, and H2 is 3.52 atm, H2O is 4.8, and CO partial pressure is 0.289. And then during this kind of the chemical reaction, there's the certain gas is forming by the reaction between the molten carbonate and the gas phase. And that actual gas is KOH. And this is the chemical reaction which is happening between the molten carbonate and the H2O gas, which produces KOH. And also, there's additional actually the chemical reaction between these gas phases, and which produce KOH, H2O. So basically, by the chemical reaction between the molten carbonate and the gas phase, it evaporates potassium from your molten salt. Okay? And so it can change the chemical composition of your molten carbonate. Okay? And which can actually affect eventually the stability of this fuel cell. Okay? So the question is, calculate the partial pressure of these two gas pieces in equilibrium condition, and then if the total pressure is 10 atm, and then if you are flowing this amount of gas continuously, and how much was actually the loss of the electrolyte per hour. Okay, and basically how does the composition of the electrolytic cell is changing with the time. That's actually our question. And to answer here is wrong, actually. Okay, let's look at this one schematically. So basically, the reactor is like, so we have inlet gas here, and then we have outlet gas. And inside here, we have K2CO3. and then Li2CO3 mixture. Temperature is 650 degrees Celsius, so it's 8, 6, 7, 8, 9, 20. Okay, and the amount of K2CO3 mole fraction equal to 0.38 in the beginning. Yep. And then activity of K2CO3 here is 0.075. So that's our starting value. And then this gas, inlet gas is H2, partial pressure is 3.52, and then H2O is 4.33, and then CO equal to 0.289. 0.289. Okay? And this gas, and then molten carbonate is having the chemical reaction. And the question is, A, what is partial pressure of these two gas species? So the first one is, if you look at it, we have K2CO3 liquid phase reacting with H2O gas, then it will produce 2 moles of KOH gas phase plus CO2 gas phase, and this we have delta G naught of this chemical reaction 1. And the second one is we have the other one, KOH gas phase plus H2O gas reacting together, and then KOH H2O gas phase. This is delta G naught 2. And we have some additional chemical reaction, H2 gas plus and then CO Okay. So by using these 4 chemical reaction, we have to calculate first what's the partial pressure of this one and partial pressure of this one. Okay. So if you look at this one, so if I assume this is in equilibrium state, delta G equal to 0, so delta G naught 1 equal to minus RT ln K, equilibrium constant. And inside the equilibrium constant, we need the partial pressure of this one, partial pressure of this one, partial activity of this one, and partial pressure of this one. Okay. This activity is given. We know that value. H2O partial pressure is given. And then this is unknown. This partial pressure, CO2 partial pressure. CO2 is not given here. Yeah. So we cannot solve just directly using the delta G naught 1 here. Yeah. So we have to find a way to get this partial pressure of CO2. Okay? If you look at now, the very last one, okay, so we have CO, CO2. So I know this one, CO, and so probably I can get this one, but unfortunately we don't know this one, O2. Okay? And now if you look at this one, we have H2 and H2O. So we know equivalent partial pressure of oxygen, O2. So we have to combine this one, this one, this one, all 3 together, yeah, to remove some unknown actually, to find out some unknown actual value here. So I'll do like, okay, so I'll take reaction number 1 plus, for example, reaction number 1 minus number 4. So then I can eliminate the CO2, and CO and oxygen is over there, plus reaction number 3. If you do this one, then we'll have K2 liquid plus H2O gas, 3 H2O, and this maybe also eliminate, and then H2, and then CO2 will be eliminate, equal to 2 KOH plus CO H2O. Does it make sense? Looks like it's okay, yeah? The geometry makes sense, yeah? Okay, so this one, now, this delta G not 1 plus delta G not 3 minus delta G not 4, yeah? So, at equilibrium, delta G of this reaction equal to 0. So, delta G naught okay, so if you enter all this one, you'll get P KOH, and that P KOH is 5.295 10 to the minus 7 atm. The partial pressure is atm, yeah? Okay, the answer is okay. For this one is okay. And then now, we know this one. Then, we have to find this one. This is easy because now we know this one. We know this one. So we can find the other one. So if you are using reaction 2, at equilibrium, same, delta G of reaction 2 equal to 0. So delta G naught of reaction 2 equal to minus ln, then P KOH H2O, and then P KOH, and then P H2O. Okay? Because we know this value and this value, so we can calculate this one. And if you do this, P KOH H2O equal to 4.246 10 to the minus 6 atm. Okay, so this is good too. Okay, so these two answers is okay. Is okay? So now, let's go to the real problem. So we know the equilibrium condition. And now the second question is, okay, so the total pressure is 10 atm. So if you just sum up this one, it's not exactly 10. So it means there's some other gas species too, yeah? For example, nitrogen gas or whatever, it doesn't matter, or argon gas. So total is 110 atm. And then we are passing about 100 liter per hour of the gas phase continuously. It means during that actually, and then if you are assuming it is always in equilibrium condition, so basically we are entering 100 liter of the gas phase, and then do the chemical reaction, and part of them is this gas, and and the rest of them would be some sort of the inert gas like N2 gas or argon gas, yeah, and then there's additional gas, and then that gas is reacting with this one, and then it make these two kinds of potassium containing gas phase, and that actually taking out potassium continuously from your molten salt. Okay, and then it goes out. Okay, so if you just learn this one, for example, 5 years, how much this will change. Okay, so we are going to calculate first, in every hour, how much of this potassium is evaporating. Okay, so if you want to do that, so now let's just look at how much actually the mole of the potassium is actually going to evaporate through this kind of chemical reaction. That's what we have to calculate. So we say P total 10 atm. Okay, and then the gas flow rate per hour, yeah, and the temperature 923 Kelvin. Okay, and now we have to calculate basically loss of this one, electrolyte. And what is this one in kilogram per, for example, hour. So that's what we want to calculate here. Okay? So KCO3. So KCO3 is reacting with all this one, and it will, so for example, if you look at this one, KCO3 reacting with H2, and it will produce KOH, and then CO gas. So slightly additional CO gas will be actually produced. But that amount is very small per every hour, so it doesn't really change any chemical reaction here. The value is almost same. It's very small, because as you can see, it's very, very small number. Okay? And same thing, KCO3 is reacting to produce this one, and also this one is reacting further. So this one is reacting further to make this one to this one. Okay? So the total, the loss of the K2CO3 is this one plus this one, yeah? Both of them. So K2CO3 will become KOH or KOH H2O. Okay? So that means if you have half mole of KCO3, it will produce 1 mole of KOH. Or if you have half mole of KCO3, it will produce the 1 mole of KOH H2O. Yeah. So if I know the number of moles of this one, half of this one will be corresponding to the amount of this one. Am I right? So loss, so N of K2CO3 loss will be half of this one will be N of KOH plus N of, okay? So this should be the, in terms of mass balance, the loss of this one is production of this one times plus this one. Is it okay? And because we are talking about per hour, every hour, the loss of the K2CO3, such rate of the moles of loss of K2CO3 is rate of the production of KOH, and then rate of the production of KOH H2O gas. Okay? You good? So now what you have to calculate is what is this value inside of gas. We know the partial pressure, and partial pressure is total pressure times mole fraction. Am I right? So we can calculate what's the mole fraction. Okay, but we don't need, we actually need number of moles, not the mole fraction. Yeah. So then, because we are talking about 100 liter of the gas, so if you know what's the total amount of gas phase, total number of moles of gas phase, now we can calculate what's the total mole fraction of each gas species. So we can calculate what's the number of moles of each species. Yeah. Is it okay? So we have to use the ideal gas law, PV equal to nRT. Yeah. So we want to calculate this one. So this one is basically number of moles of the total number of moles of the gas species times gas times mole fraction of the KOH. Yeah. And same thing for this one is number of total number of the gas species per hour times mole fraction of the KOH H2O. Okay? And this one is from the partial pressure. So partial pressure of the KOH equal to P total times mole fraction of KOH. Okay? So it means X KOH equal to P KOH divided by P total. And P total is 10 atm. So this is 10 atm. So we know this value. So we know this value from the equivalent calculation in the previous one. And so we can calculate this one. So if you enter this one, so we know this value, but the only unknown value is this one. Total number of moles of the gas, which is passing through this actual reactor per hour. Same thing. So we can do this one, yeah? So now, how we calculate total number of the gas species? Yeah? So PV equal to nRT. So ideal gas law. And the amount of volume passing through, so the rate of the volume which is entering into this system and then going out is directly related to the amount of the number of moles of the gas species entering here. Yeah? So total. Is it okay? Is it good? So P total 10 atm, V 100 liter per hour equal to N total per hour, we don't know this one, and then gas constant. Yeah. Times T. Okay? Then you get N total. And total is 13.21 mole per hour. So it's quite significant number of moles of gas per hour. Okay? But if you look at actually this mole fraction here, so this is partial pressure, and the mole fraction of the KOH H2O is 1 over 10, yeah? So you have to divide this one by 10 again. And same thing, for this one, you have to divide this one by 10. So 10 to the minus 7, 10 to the minus 8 mole fraction. And then you have about 10 to the 1 mole fraction is multiplied here, yeah? So it's about 10 to the minus 6 number of moles of this gas species is producing per hour, yeah? So if you look at it, total, so N, so this is actually same as N, total in the K in the gas phase, number of moles. This is both of them containing 1 mole of the potassium. So this is basically the two together is total number of the potassium species inside of gas phase. yeah, potassium element in the gas phase. So N total, Nk in gas phase, so this one, these two together is about P total, so this, if you do it, 5.27 blah blah blah. Let's do it in this way. So if you have 1, 10, and 100, and etc. So this will be eventually 4.7755 10 to the minus 7 times 13.21 total value. I'll just give you the final answer. 6.308 times 10 to the minus 6 mole per hour. So this is the value. So in terms of the loss of this one, now you have to actually divide the multiply and but this is the other way around, yeah? 2, yeah? 2, yeah? I'm sorry, it's 2, yeah? It's not half, yeah? So if I'm losing 1 mole of K2, it will produce 2 moles of K, yeah? All right? I'm sorry about it. I make you confused. So if I lose 2 moles of the potassium, K2, CO3, it will produce 2 moles of the potassium species, gas species, monopotassium gas species. You understand what I mean? So if I have 1 mole of oxygen, it will produce 2 moles of the mono-oxygen, yeah? So the mass balance is 2 times of this one, should be same as 2 together. Is it okay? Make sense? No? So, let's do it mass. So I have 1 mole of K2CO3. I have 1 mole of K2CO3. And then it reacts with blah, 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 and it will make 2 moles of KOH, yeah? So, number of moles of KOH produced is 2 times of the loss of the K2CO3. Okay? Is it okay? Not half. I'm sorry, I was confused. Is it okay? Yeah. So now we know this one. So this is this one. So final loss of the K2CO3 is half of this one. Yeah. The loss of the K2CO3 will be, so we know this value, and so this loss is half of the potassium actual production rate in the gas species. Is it okay? So if you do that, the answer is slightly different. So now, if I apply this one, the N is so now I know the number of moles of the K or K2CO3 loss, and now you have to multiply this one with the molar weight of K2CO3 to know how many kilogram of the K2CO3 is, removed from the actual your system. Okay, so eventually N okay, so molar weight is gram per moles. So if you multiply this one, you know how many actually the kilogram, how many gram of K2CO3 is lost. So divide. So this is gram per mole. Okay, so if you eventually convert this one in kilograms, so it will be, or even in the gram, so 4.355 times 10 to the minus 4 gram per hour. So this is the amount. Okay? So if you think about one day, it's 24 hours. And then if you think about 1 year, 20 times 368? 365, sorry. 365. And even 1 year, by 1 year, it's just few grams of the actual loss. Okay? And if this is like several hundred kilograms of the molten salt is inside of this kind of reactor, the real loss by the chemical reaction is very, very small. So over the 10 years, there's almost no change. Okay? You good? Yep.
I'm still confused with the coefficients in the
This one.
So the left side we have 4 rotation axes.
Yeah.
To the right side we have 2.
Yeah. Let's think about it again. So you are losing actually, so I mean, you have the balance here. So I'm losing something and I'm gaining something. Yeah. So if I'm losing 1 mole of K2CO3, it can produce 2 moles of KOH, for example. So let's forget about this one. Let's assume there's only KOH. Okay. If I'm losing 2 moles of K2CO3, it will dissociate into the 2 moles. 1 mole of K2CO3 will dissociate into the 2 moles of the KOH. Yeah. So amount of KOH produced is same as 2 times of the loss of the K2CO3. It makes sense? That's why it's 2, not half. One more of this one will produce 2 moles of this one, yeah? So, 1 mole of this one will produce 2 moles of this one. So, number of moles of this one producing is 2 times of this one, of this. So, this one is corresponding 2 times of this. I know even I was confused when I write down. Is it okay? Make sense? You don't know. So you think about, we lost, so when you did actually the gas-gas chemical reaction in equilibrium, okay? So we say that we write what's the initial gas species, what's the final gas species. Do you remember this? And then by the chemical reaction between these, some of the gas species, we have to define kind of the, mass balance of the final gas species. So let's assume that I'm losing 2 moles of, 1 mole of K2CO3, then it will produce 2 moles of KOH, yeah? So amount of KOH should be 2 times of the loss of this one. Yeah? Is it okay? If you look at just mass balance like this, it doesn't make sense, of course. I know what you mean. But mathematically, the loss and the production is same, so it should be like this, 2 times. Mingyong, is it okay? Good? Okay? Good. This is the one of the questions I really want to do it in the last minute because it takes a little bit long time to explain the whole thing. Okay? I like this type of question. This is the real one, yeah? It's more like real type of the real process. So one of the your midterm exam or final exam, if you look at now, you can even look at some of the final exam. And for many years, I actually introduced similar type of the question. So one of them is, let's assume we have fission process, now I am actually injecting certain amount of gas species and then calculate what's the production rate of the magnesium through the fission process. So if you know the partial pressure at the equilibrium state, and then if you know how much actual gas is passing through, you can calculate how many moles of the magnesium is actually produced from this kind of gas species, gas phase. Okay? Good? Okay, now let's go back to the more theoretical part. Are we doing chapter 3? Am I right? What's the actual chapter number? I'm sorry. I forgot. Chapter 4. Chapter 5? No. Text. Chapter 3, Solution Thermodynamic. Okay, and then we did Gibbs energy, solution. No, this is the question in the questionnaire. So how much we did? Chapter 4, and then subheading should be 1. So activity, that's what we have learned, and then 2. And so we have to do 4. Okay. Chapter 4. So this chapter is different chapter actually than the exercise, homework exercise example, yeah. So this is more kind of the theoretical part. Chapter 4, so it's a liquid. Solution, and then this is now number 4, 3 or 4, whatever. Now partial. Chapter 3. So we are still in chapter 3 then. Partial thermodynamic. So we'll learn this one. Okay. So partial thermodynamic property. We already learned what is partial thermodynamic property because when I introduce actually solution thermodynamic, so for example, Gibbs energy of solution is partial Gibbs energy of A and mole fraction of A, partial Gibbs energy of B, mole fraction of B, yeah? So that partial Gibbs energy of A is partial thermodynamic property, one of the partial thermodynamic property. So when you have any kind of the thermodynamic property, so let's assume in this way. So I have any kind of thermodynamic property. Of solution. So this is when it's solution. So for example, this could be Gibbs energy. Well, this would be enthalpy, entropy, even molar volume. etc. Even total pressure. Okay? So whenever you have some thermodynamic property of the solution, so Y theoretically solution, and this can be expressed by the summation of the partial thermodynamic property of the all the species in the system on the solution, sorry. So Y of I and Xi. And then this Yi, Xi, in order to show that this is really partial property, sometimes people actually put the bar on top of actually this property here. So this one, we call it partial thermodynamic property. Okay? So it's nothing special. We have learned, we have used this actual concept all the time. As I mentioned, one of the concept is total Gibbs energy of solution, Gibbs energy of solution equal to the partial Gibbs energy of A, mole fraction of A, partial Gibbs energy of B, mole fraction of B. That actually GA, GB is partial Gibbs energy. Okay, partial thermodynamic property. Okay? And why we actually learn then specifically partial Gibbs energy is between the partial Gibbs energy there's a relationship. Okay? So, for example, one of the things we want to derive in the end of this class is if I know the partial thermodynamic property of the one species in the binary system, so let's assume I have A, B binary system. If I know the one of this partial property with the composition, then I can theoretically calculate what's the partial Gibbs energy, partial thermodynamic property of the other species. Okay? That's what we call it Gibbs-Duhem relationship. Okay? So we want to actually derive this Gibbs-Duhem relationship. That's the reason actually we are introducing this partial thermodynamic property. Okay? So one of the most easiest one we can think about the partial thermodynamic property is molar volume of the solution. Solution. Okay? So most of the time in the book, if you look at it in the book, the example is always same. So let's assume we have two kinds of species and making the solution. I mean, this is a little bit physical solution, but it's okay. So let's assume I have here, and this is soccer ball. Okay? So it's a very big ball here. So this is A. Okay? And I'm mixing this one with B, which is very small ball. For example, golf ball, so which is very small. Okay? And then if you mix it together, and then let's assume this one is VA, and this one is VB. In order to say this is the pure A, so let's just put the, special mark, VA naught, VB naught. Okay? If you make a solution, so V of solution, is it going to be same as VA naught, mole fraction of A, plus VB naught, mole fraction of B, or not? So if this same, it means kind of ideal solution, yeah? But most of the time, if the size of the ball is completely different, then this cannot hold. Yeah? Because small ball can go inside of the bigger ball. Basically the empty spot inside of between the actual bigger ball. So the molar volume will not be same as summation of the pure A and pure B volume. Okay? So then people say that, good, I can understand this one. Then how do you want to actually define the molar volume here? Okay? So we want to define the molar volume instead of the just summation of pure A and pure B. We want to define this one as a V of molar volume as VA XA plus VB XB. And then this one is, we call it partial molar volume of A species at the given condition. And same thing, this one is partial molar volume of the B at the given condition. Here the given condition means, okay, at the given temperature and given pressure plus given composition as well. Given composition as well. So why I say given composition is, okay, so when you have, for example, about 99 ball is A, and when you're adding only one ball of the B, I mean one ball of B wouldn't even change the molar volume, yeah, because it can enter into the one of the spot, okay? And then now if you keep talking about 50%, then some part of this molar ball, small ball can go inside of the bigger, actually between the empty spot between the actually bigger ball, but some of them cannot go because all the empty spot is already occupied by the smaller one. So it starts to increase the actual molar volume. Yeah, you can see the actual contribution of molar volume by the B balls. Yeah, so molar volume of A and B is not simply changed by the temperature and the pressure. It can be also changed by the composition of the system, composition of solution. Okay, so that's actually that should be considered inside of the partial molar volume of the species. So partial molar volume of species is function of temperature, pressure, and the composition. Okay? So it's not constant. Partial volume can be changed depending on the composition. Okay? So then we have to define really, okay, how I'm going to really define the partial molar volume then. Okay. So as an example, partial molar volume, how we actually define this one is like this. Okay, so I have this kind of solution here. So this is AB solution. Okay, it could be pure A, pure B, or any kind of composition of AB at the given temperature and the pressure. Okay, now I'm adding certain amount of D and A amount of new species. So I'm adding A species, but very small fraction of A into this solution. And then we can measure change of the volume, delta V. So this is dV of solution basically. So by addition of this one, it can be shrink or it can increase. Whatever it is, I don't care. But we will see the difference by addition of this one. At the constant temperature, constant pressure, and we are not even adding B, only A. We are adding only A. So definition of the partial property. In this case, partial molar volume is VA, so partial molar volume of A at the given composition and temperature and pressure equal to change of the total volume, so solution, by addition of small amount of the A species in the system when T, P, and NB is constant. That's the definition. Okay? Then, basically, okay, molar volume is this because this is constant at the given composition and given temperature, this times of dNA, yeah? dV equal to VA dNA. Okay? So we can write same thing for the dBV, okay? So by definition now, so I mean if you just assume this one, now by definition, V of solution equal to VA NA plus VB NB. If you just assume that this is 1 mole, then we can say VA XA plus VB XB, and we say that this is partial molar volume okay, and then from this definition, dV equal to VA dNA, so and this is VA XA plus VB dXB. So if this is molar volume, then we can define in this way. Okay? So it's a per mole of solution. So in total, 1 mole of solution, then we can define in this way. So now, actually there's something strange. So I can say in this way, or if you like, here I say VA, and partial property I typically say V, and then over this actually the bar, over the actually the symbol. So if you like, you can even say VA bar, VB bar, VA bar, VB bar, if you like, okay? It's the same, okay? So when you say VA not, it means pure A molar volume, pure B molar volume. So this is already, all this symbol is partial thermodynamic property, partial molar volume in this case, of species in the system. And then now if you look at actually 2 equations here, there's actually something strange. I mean, this is definition, we define in this way. And this is also another definition from the theoretical point of view, okay? And then in order to match these 2, we can actually find one condition. Because if I make a derivative of this one, it should be like this, yeah? If I make a derivative of this one, dV, actually if I make a derivative of this one, I have to make a derivative of this one, so it's VA dXA plus VB dXB, assuming that VA, VB is constant, but however, it's not constant. It can change with the composition, yeah? Am I right? It can change with the composition, as I mentioned before. So this should be also this can be also, we have to apply the derivative of these 2 as well. Okay? So then XA dVA plus XB dVB. Okay? Now if you actually compare these 2 equations, this will give you that. Okay, so V solution is this one. Okay, this one. Then it means this one should be 0. Am I right? XA this is very important actual relationship. So it means somehow if I know the A, derivative of A with the composition, and then I multiply this one with the mole fraction of A all the time, then I can get the VB, derivative of B, how does derivative B should be changed. That's what it is. So if I know the A property, I can get the B property. Okay? So if I generalize this one, this is like this. So y of solution, as I mentioned, total thermodynamic property of solution is sum of yi xi. If you like, you can put this one, or you can say that yi xi, same thing, okay? So just, this is one condition for the partial thermodynamic property. So a relationship between partial property and then total property, okay? And then there's another relationship here, that one. Sum of mole fraction of I and derivative of yi equal to 0. So if you like. Okay, just different symbol, okay? It's same meaning, partial property. And especially this one, we call this one as Gibbs Duhem relationship. All thermodynamic property have to satisfy this condition. Okay? This is the one of the criteria we are using in thermodynamic. In my world, in thermodynamic calculation, for example, or thermodynamic measurement, the two partial property, if you measure them independently, partial property of the two elements in the system, if you measure it separately or independently, this should keep this relationship. Otherwise, one of them is wrong. So we can test, okay, consistency of the two thermodynamic experimental data. Okay? One is, and also the other way is, when people actually try to measure something, and then if that actually thermodynamic property is very difficult to measure it, they measure the other one, and then back calculate, derive actually the thermodynamic property you want to actually get by using Gibbs-Duhem relationship here. Okay? This looks like a little bit difficult to understand how to derive it eventually, but if I know that this one as a function of composition, then you can actually enter it here and then make a derivative and then you can do it. Okay? That we call it Gibbs-Duhem relationship. Okay? And to say frankly, if you are not doing my type of the work, most probably you never see this one in the future anymore. Okay? But at least it's worthwhile to remember the name, Gibbs-Duhem relationship, because from time to time people say that, okay, based on the Gibbs-Duhem relationship, this doesn't make sense or this makes sense. Sometimes people actually saying this way. So at least you have to understand what's the meaning of the Gibbs-Duhem relationship. Okay? So if I look at this one again, then I'm going to derive the now modified Gibbs-Duhem relationship, which is more applicable one. Okay? So before that, let's look at this one again. So what's the meaning of this partial property? If you look at now graph like this, so for example, let's assume this is y of solution, and this is composition of xb. So it's A is here, B is here, okay? And let's take any kind of the curve, okay? And this one is the YB not basically pure, yeah? And this point is YA not pure, okay? At any composition, and this is at the given temperature and the composition, temperature and the pressure condition, okay? At any given composition, here, for example, this relationship here, partial property here, can be calculated by using tangent line at that point. So if this is this one, if I draw the tangent line, this point here is YA at this composition. So partial property of A at this composition can be taken by this intersection point of the tangent line. Okay? And this one is YB here. And then if you actually take the other composition here, then if you draw the tangent line, this is now YA, this is YB. Okay, YA, YB is changing with the composition basically. Because I say this one is this times of this linear actually summation, yeah? So this point, so for example this point is this times of this amount. This amount. So that's actually this one. This is mole fraction of, so let's take it in this way. How can I say that? So this point, in order to get to this point, this is Y of solution. I want to have summation of some partial property and the mole fraction of XB. So XB is this mole fraction, yeah? So if I take this one and mole fraction of B, this will give you this amount of contribution. And then if I take XA, so this XA is now I think about 0.3, for example, 0.7 of B, 0.3 of A. And if I take that actual contribution of this one, multiply this, and it will give you 2 together, will give you exactly this point. If it's half and half, exactly half and half, if you are very close to this one, A contribution should be bigger than B contribution, and the other side, B contribution should be bigger than A contribution. Okay? If you really do the mathematically, you can find it easily about this relationship. Okay? So this is basically partial thermodynamic property. So whenever you have solution at the given composition and the temperature and pressure, and if you draw the tangent line at that point, and 2 intersection point in the your both y-axis side is corresponding to the YA, YB, partial thermodynamic property. Okay? You good? Now, one of the actually this one is Gibbs energy of solution. So let's just take one good example, one very important example for most of the our thermodynamic calculation. Let's assume this is Gibbs energy G of solution. Okay, this is A and B, and this is basically G pure A, G pure B. Okay, and then let's take any composition here and then make a tangent line. So this is GA and this is GB. And I explained this one last time, but I want to actually repeat one more time. So in thermodynamics, we say that Gibbs energy, partial Gibbs energy of I equal to Gibbs energy of I pure plus correction term. Yeah. So Gibbs energy of I in the solution is pure Gibbs energy of I plus correction term by the surrounding in the solution. That is RT ln activity of I. Okay? So from this graph, basically, I know the partial thermodynamic property of B at the given composition, at this composition of solution. My partial Gibbs energy of B is this one, and my pure Gibbs energy of B is this one. So this difference, GB equal to GB naught plus RT ln activity of A. So activity of A is lower than 1, of course. So basically, this is negative term. So this minus this amount, that is corresponding to your partial Gibbs energy of B. So this difference is RT ln activity over the B. Same thing for the other side, yeah? Okay? So when you do your final homework number 5, you have to know this relationship. You start to actually finding all the activity of the solution, activity of the system, depending on the composition, by using this graphical way. Okay? You good? Okay, now let's look at a little bit more this the Gibbs-Duhem relationship. So Gibbs-Duhem relationship, I say, for example, for binary solution, this xa, ya, dya plus xb, dyb equal to 0. Ya, yb could be any kind of thermodynamic property like Gibbs energy, enthalpy, entropy, molar volume, whatever it is, okay? You good? And when you have this one, now I want to modify this one to get new function. Okay? So what I want to do it is, okay, so at least we know that, so xa, ya plus xb, yb is y over the total solution, yeah? So we know this one. This is definition of the partial thermodynamic property. Okay, and then can you get this one? XA mole fraction equal to 1. And then if I make dxa 0. It makes sense? When XA is increasing, XB is decreasing by the same fraction. So dxa plus dxb equal to 0. That's okay, yeah? You got it? So let's take this relationship and then try to modify this one and get the new function. So if you do this one, so let's make what should I have to do? Let's take from here. Sorry. Let's take from here. So xa, ya, xb, yb equal to y solution. Am I doing okay? yb. What I want to do? What I want to do? I know what I want to derive, but I don't know how I have to derive first in the beginning. Oh yeah, sorry, now I understand. Okay, I'm sorry. So dy, so let's go back again. dy so we derive one of equation like this, yeah? I'm sorry about this. So we have to combine all this one actually to find actually, to modify this equation. So this is the starting point. So the solution gives, so when I actually define the partial thermodynamic property, so y, dy equal to ya dxa plus yb dxb. Is it okay? So let's start from here. Okay, now, if I say YA, so if I leave the YA and then if I move all the other one and then divide by DXA, so this will be minus YB DXB DXA plus dy over dxb. Am I right? And these two is minus 1, so this will be plus. Okay? So this will be yb plus dy over dxb. Is it okay? And then now I multiply xb in the both sides. So this is ya. And then now xb, multiply this one. Entire system, so then it will be xb ya equal to xb yb plus xb dy over dxb. dxa. Is this the one? xa. Okay? Now, let's look at this one. So, YB. So, YB. So, according to this relationship, so YB is YB, YX, YA. So, XB here is, no, I don't have to do this one. XB, YB. YB is Y solution minus YA XA divided by XB. Is it okay? And then if I multiply this one, XB will be cancelled out. So this one eventually XB YA equal to, so YB, XB is cancelled, so it's Y solution minus YA XA plus XB dy over the dxa. Is it okay? And now let's move this one to the other side. Then it will be YA times XA plus XB, yeah? XA, XB equal to 1. So this will be YA equal to Y of solution plus XB dy solution dxa. Is it okay? So eventually we get this one. This is modified Gibbs-Duhem relationship. Some people say that this is the simply Gibbs-Duhem relationship too. It's the same, basically. This is Gibbs-Duhem relationship, and this is another form of Gibbs-Duhem relationship. So when you actually look at this one, it's a little bit difficult to how to actually get my partial. So this one, basically, if I know the partial, I can get another partial. That's actually what it means inside of here. But this one is, if I know the total, I can get the partial. If I know the total solution property, then by the derivative of this one with the mole fraction of A and then multiply the mole fraction of B, I can get the partial property of A. So if I want to know the partial property of A from the total solution thermodynamic, so if I know the, for example, if I know the thermodynamic property of solution as a function of composition at the given temperature and the composition, given temperature and the pressure, then I can make a derivative of this one with the composition and multiply with another composition component here. I can get my partial thermodynamic property. That's what it means. And that's actually graphical same as this relationship here. Okay? So I can get mathematically in this way. From the source, partial thermodynamic property can be calculated from the total solution thermodynamic property. Or this one is, I can calculate one of the partial thermodynamic property from the other partial thermodynamic property.